Right, okay, it's Friday night, so I'm doing this. Unicorn has commented saying, can you please do a video of all likely equations, such as volt drop, as most of us are rusty, thanks. And I've put, okay. Right, I'm going to need a scenario, though, because I need to, every time you get a question that uses, obviously, a formula or maths, there's going to be some data given, and so I have to have some reference data. And what I'll try to do is, I may not do them in the most common order, but I'll do them in an order that I can then use them. So the scenario I'm going to use, I've got here. It should be visible. So we have yeah. This scenario has been just completely made up by me right now. I haven't even worked with this, so I'm going with a 7 kilowatt 230 volt door heater curtain, air curtain above the door. Wiring system is surface clipped above a suspended ceiling. Cable type is a copper multi-coil steel wall armor, 70-degree thermoplastic. Ambient temperature 35 degrees, and is grouped beside two other circuits of the same demand. Protected device is a Type C BSEN 60898. It's 27 meters in length. Right, so the formulas that we're going to get. Let's start with a very obvious one. So we have the whole coordination. So we need to remember this principle here. Okay, and this one. Now these come under protection against overload current. So protection against overcurrent is chapter 43, and in there it splits between 433 and 434. In 433, which is overload current, you will see this. It doesn't display it this way. It displays it in a way that is very wordy, but the assessment will display it this way. So what you'll have is you'll have a scenario such as if IB is equal to 31 and IN is equal to 33 and IZ is equal to 28 kind of thing. And then you'll have another one, and the rule of thumb is they'll be displayed so they have different numbers, but the values will need to climb from there to there and from there to there. So they should go up and up. So the IZ should be the largest of the values and the IB will be the lowest. We'll explain that in a minute, but that's one of the more basic formulas. It's not written in the regs book, but it's covered in 433. I've actually just flicked to it straight away. So here, 433 protection against overload current, and 433.1.1. It's the wording of all this here. Let me just zoom in. The rated current setting of the protected device IN is not less than IB, and IN is not less than Z, and then the I2 and the IZ there. So that's the first area that could illustrate itself as a formula. Okay, another one. Well, there's one that we should be fairly familiar with, and this is that the ZS is equal to the ZE plus the R1 plus the R2. Obviously, this isn't written in the regs book either, but it's in the exam. What will happen is it will display, ZS is equal to 5 times ZN, or ZE equals R1 plus RN times ZE. All sorts of fictitious nonsense. Obviously, we need to know this one. Now, if you're unfamiliar with that, this is what we would call a question that really just challenges your electrical knowledge. There's nothing in the regulations that kind of expresses it or shows you the formula. Okay, but we understand that the R1 plus R2 is the internal wiring. The ZE is the external wiring. We know that because we see that in section 313, the supply characteristics in part 3. That makes the ZS, which we cover in chapter 41, the total earth fall loop impedance. So the total loop is equal to the internal loop. The total is equal to the internal plus the external plus the internal there. So the external plus the internal. Okay. Total is equal to external plus internal. Okay, if you aren't familiar with that formula, you really need to get that one on board, because that's just so, that should be an easy one to be fair. There are many formulas in the regs book that use this, but they look nothing like it. Okay, they may look like this. Yeah, or they may look like this and this and this. That it's simply Ohm's law. Ohm's law is used a lot through the regs book, throughout part 4 and in later parts. It's very often used when it's trying to ensure the touch voltage does not go over 50 volts when we have RCDs and supplementary bonding, for example. So understand your simple principles of Ohm's law. Now let's get a little bit more complicated. In the scenario I have on the right, we're going to start thinking about cable calculation. And if we were to do that, we would say that IB is equal to P over V, power over voltage, which is equal to 7,000 over 230, which I haven't got a clue. Hang on. So 7,000 over 230 equals this. 30.43, we'll call that. Fine. Okay. 0.43, something like that, right. And if you remember the coordination that we saw a minute ago, yeah, IB must be less than equal to IN must be less than equal to IZ. We know that the IN, which is the protective device, must be greater than IB. So we're going to go in this scenario with a 32 amp. Type C. Fine. In the exam, you're not going to have to do a whole process such as this, but what you will have to do is a part of the process, such as the volt drop part, such as the design current part, or maybe the selection of the rating factor part, or maybe the selection of a cable size determined by your tabulated value of current carrying capacity. Any one of those pieces of this puzzle could come up, so have some good understanding on this part. So if we have the IN of 32, we now need to make sure, so we've got the IB of 30.4, we've now got an IN of 32, we now need to make sure the IZ is a cable that can carry 32 amps. But before we do that, we must understand that it accommodates anything that may affect its ability to give off heat under load, such as rating factors. Now let's remember the rating factors are mostly in part 4. Some are mentioned in part 4. There's some in part 4. There's the CC and the CF. In Appendix 4 is where they really live. Okay, that's where they really live, with the exception of one, which is the CI, which I think is in 523 or somewhere around like that for the insulation. Okay, so in this scenario that we have here, though, we have an ambient temperature, which we'd use as a CA, and we have a grouping factor, which we'd use as a CG. Those are both in Appendix 4. And in this case, I know that I need to go to table 4B1 for the CA and table 4C1 for the CG. What I would say is, if you're tabbing or whatever, is do think about with your tabs. Maybe if you need to, think about putting tabs for each rating factor. When I did my exam in 2008, the 17th edition, I had a few tabs along the top, maximum ZS, adiabatics. When it came to this area, though, I was like, oh, crikey, I'm everywhere. So I went down the side of the book with a CA, a CI, a CZ, a CC tab. Because Appendix 4, there's so much reference information in tables, the volt drop table, the current carrying capacity of cables tables, the rating factor tables, but it all looks the same. And, unless you're really experienced with the book, you will end up just flicking away with the hope of luck to find it. So it might be worth just tabbing it or referencing the numbers on your pages or something. All right. So in this example, I need to find that. So I need to find these rating factors. So I'm going to jump to the appendices. So that's Appendix 3. I know when I'm in Appendix 3 because I can see the time curves, you see. I have these little visual cues. Right, I'm now in Appendix 4, table 4B1. Bit quick when you know what you're doing, isn't it? Right, ambient temperature is 35 degrees. It says in the scenario 70 degree thermoplastic. So with that in mind, here's table 4B1. 70 degree thermoplastic, 35 degrees, 0.94. So that's my factor for 4B1. Now 4C1 is on the next page here. Now it says in the scenario that it's grouped between two other circuits of the same demand. The reason it says of the same demand is so I know I don't have to pay attention to note 9, which tells me about the 30% of its grouped rating. So it's a reference method C, and there are 3 of them, so that's 0.79. Okay. Okay, so this is obviously simulating, you know, we have like an armoured, and then an armoured, and then an armoured, and in the case of the armoureds, they are less than 2 times their diameter apart. Then grouping is applicable. Right, so moving forward, I have to find a tabulated value, and that is the IT. If you go to Appendix 4, you'll see that IT symbol is used. And bear in mind, overload protection isn't needed. I'm still going to stick with the one that is used in the exam, which is IN over the applicable rating factors, CA times CG, so that's 32 over 0.94 times 0.79. Okay. Again, my math is I've had a drink, it's a Friday, I need a calculator. Alright. What was it? 0.79 times 0.94. I'm just working at the bottom line first. 0.7426, okay? And then I'm going to take 32 amp over that, 0.7426. So 32 amp over 0.724, 7426, it's a bit of a home there, is an increase in current requirement of, okay, nearly 10 amps. So it's going up to 43.1 amps. Alright, so I now know that the IZ, which was here, needs to be at least 43.1 amp. I now need to select the cable, and that's where I'm going to go back into Appendix 4 to the cables. Now the scenario says it's a 70-degree thermoplastic multi-core armoured steel or armour. So let's go there. Reference method C, single phase. This is where the page turns sideways. Doo-doo-doo. And we are nearly there. Oh gosh. I want to rotate the book around, goes to the beginning again. There we go. There we go. Right. Let's get to the copper. Alright. 90 degrees, no. 90, 60, 90, 90, 90. We want 70. 70. Okay, that's twin and earth flat, no. Multi-core armoured 70-degree thermoplastic. This is us. Okay, so we're still our armour, so it's armoured 70-degree thermoplastic. We want reference method C. And as we're a single phase cable, we want this one. And we want the next value above 41, which is 49 amp, 6 mil. Okay. And that makes IZ 49 amp. Now I'm going to update this information over here. Okay, so we have 6 mil cable. IZ equals 49 amp. IN equals 32 amp. I'm going to refer to that later on. Okay, and that'll do. That's all we really need. Okay, so that's to get to this point. Now, obviously, we need to verify volt drop. Now, this is a very popular question. So what I first of all will need to do in this scenario is get the volt drop number. That's going to be, we're back on this table here, 6 mil. Okay, that's on the adjacent page here. The volt drop in per ampere per meter for, in our case, we're not DC, we're not 3-phase, we're single phase, 6 mil, 7.3 is our value of millivolts per amp per meter. 7.3. So I'm going to write that. That's my reference for now. Let's clear this up. And that's just showing the IBINIZ bit with the tabulated value. But this is the more common one. Volt drop. Volt drop is equal to the millivolt per amp per meter number. That's the number we just got. Yeah, here. 7.3 is that value. Over 1,000. Okay. So, bearing that in mind, let's just get rid of that. That means the 7.3 millivolt per amp per meter times the per amp, and we got the design current to be, I've just deleted it, 30 amps, wasn't it? I should have written that one down. 7,000 over 230, 30.43. I'm going to just do that. That's the one I didn't put down. IB equals 30.43 amp. Okay, and we times it by the IB because that's obviously the current being pulled. We do not times it by the IN. All right, so that's going to be 30.43 times the length. Now the length is given in the question as 27 meters. 27 meters, and I divide that by 1,000. The reason I'm dividing it by 1,000 is I don't want a millivolt value, I want a volt value. Okay, so alright, so 7.3 times 30.43 equals that times 27 equals that over 1,000. 5.997, so it's basically 6 volt, isn't it? Alright, 6 volts. So the question is now, is that acceptable? And you may have to obviously do that, but in the regs exam, you won't. You'll have 4 answers which are a voltage, and you've got to match it to this, and that's it. But for completeness, if you were needing to verify that, you would need to go to table 4AB, which is also in Appendix 4, way further up. Sorry, I turned the book around. There we go. Here. Yeah, 6.4 within Appendix 4. Familiarity with Appendix 4 is very, very helpful, okay? So, low voltage from a public supply, other use, it's 5%. 5% of 230, well, 10% of 230 is 23, so half of that is 5%, half of 23 is 11.5. So, yeah, 6.4, 6 volts is fine. But you're going to have in the exam something like this. You'll have a question such as a load of 30 amp on a 32 amp breaker. Okay. It may probably then tell you a cable of 7.3 millivolt per amp per meter for a length of 27 meters. It might give you all of this. So all you've got to do is first of all remind yourself that we do not use IN. So if you see this question, it has a breaker in it, get that out of your head. That's a red herring that they put in there on purpose. So you just multiply the numbers together. Okay, and to be fair, that will give you a number. Obviously it's 1,000 odd, but it'll be one that matches your answers. Because when you divide it by 1,000, all you're doing is moving your decimal. So once you've multiplied these three numbers, you should see a number that looks very much like your answers. All right, with the volt drop. The volt drop formula is not written in the regs book. It's in the on-site guide, but it's not in the regs book. So do make sure you've got a good understanding on that formula. Okay. Alright, so we determined that this is okay. Now, we wanted to then think about something else. And that is this wonderful formula here that appears in protection against fault current. T is equal to K squared S squared over I squared. Now that one is about ensuring that the time that it takes for the conductor to reach its final limiting temperature, its final temperature, not its operating temperature, is much longer than the disconnection time. So for the sake of sanity, in our example, we'll call this a TN system. Alright, which means we've got a final circuit. Now let's remember part 4, chapter 41. We've got a final circuit now. And this final circuit on a TN system is connected to equipment that is not greater than 32 amp, because it's 32 amp. That means the disconnection time for this requirement is going to be 0.4 seconds. Disk time. Okay? We need 0.4 seconds. So we need to make sure the time we achieve here in this calculation is more than that. Now, something we do not have in this calculation is a value of K or a value of fault current. Okay, now sticking to the scenario that we have S, because we know that S is the size of the line conductor, which we are now saying is 6 mil. Fine. What is K though? We get K from chapter 43. So if I go to chapter 43, that's where this is. Alright. Now you're gonna when the question is worded, it's gonna say that probably the words protection and fault current. And that immediately should trigger you to protection gets an overcurrent, chapter 43. Force protection overcurrent is 4.3. And within there, 4.3.4, which is the fault current part of 4.3. Hopefully that's kind of how you're referring to the book. If you're looking at the appendices, then fine. But let's get to that. Overcurrent, fault current. So it's introduced here. There's the formula. And the K is taken from here. Now in your exam, you may be given all the information and just be asked to put it into the formula, or you may be asked to find the factor for K. That's about all they do with this. So in our example, we're sticking to the same example we've used already. Steel wire armor, 70 degree, thermoplastic, 6 mil. So with thermoplastic, 70 degree, less than 300 mil, because it's 6 mil. The initial temperature is 70, that's the operating temperature, and the final limiting temperature is 160 degrees. For copper, the K is 115. So 115. Now I is a bit tricky, because for the sake of exams, we'll go with the current that achieves disconnection of the protective device, which I'm going to find in Appendix 3. In reality, though, this could be a bit more current due to parallels and due to real-time scenarios, so you should always re-verify this. But let's just go to the curves. I've got to flip the book around again. Oh, God. There we go. All right. Do. Oh, that's the wrong button. That's the button. I was just refreshing it. There we go. That's upside down. Boom. There we go. Right. So, we're looking at this area of the book, the Appendix 3 time curves. We've got the different fuse systems, and we want a Type C BSEN 60898, because that's the scenario. So there's the Type B. We go to the Type C. 60898, and we selected an IN of 32, so we see here 320 amp is the required current for achieving disconnection, and we know that it's a 0.4 second disconnection time, and we know that 320 will easily do that, so we're going to go with that. To be honest, a little bit less current, probably still trip it in that time frame. So I is going to be in this case 320 amp. So let's translate to the formula. The T is equal to 115 squared times 6 squared over 320 squared. Right. Okay, let's try that in this. Obviously, another thing that is important before your exam is familiarity with your calculator. Alright. Do make sure you bring your own, because they'll probably provide you with something that's tiny, and in some cases doesn't have enough digits on the display, which is really infuriating when I see that. Okay, so 115 square times 6 squared, which we know is 36, equals that, over the value of 320 square equals that. 4.649 seconds. So yeah, 4.6 seconds. It will take 4.6 seconds for this 6mm cable, when subjected to 320 amp, to rise from 70 degrees up to the final temperature of 160 degrees. Okay, that's the point. So when a fault occurs, 4.6 seconds is the time to climb from 70 to 160. What will happen before that though? It'll disconnect, because the 0.4 second disconnection time. So that's fine. That's an example of that math there, and that works out absolutely fine. Let's go to another one, and let's use the transposition of that formula, the adiabatic. The adiabatic is just a simple calculation to verify the protective conductor is sized to accommodate the mechanical strain and the electromechanical impact of a large fault current. So in this example, I is again the fault current. So that's going to be 320 square. Same amount of current. T is the disconnection time over here. So T is equal to 0.4. That's how long that current is there for. K is the same. It's 115. So we'll go into the formula. And again, in your exam, you may just have to find the use of the formula. They probably won't ask you to get all the information. Because you've only got 2 minutes for each question, technically, haven't you? So okay, so 320 square times 0.4 equals square root the top line. Okay, don't square root the whole thing. Then over 115, 1.759. So we'll call that 1.76. So this equals 1.76. There's no such size cable as 1.76, so that'll have to go up to 2.5 mil as the minimum required protective conductor size. Now it's most likely that our steel armor, being single face, is going to be a 3-core, so it'll probably have within it a 6 mil protective conductor. So good. Alright, good. Just practice playing with the formula, practice punching in the numbers. What's next then? Well, maybe we should go back to chapter 41, to the ZS's. There's actually a couple of places that we need to refer to this, but you need to first of all understand if it's asking you the maximum ZS or the maximum measured ZS, because there's a difference. Alright, now if I go to chapter 41, all I'm going to find is this one. And this is where I say it looks a bit like Ohm's law. Okay, because, you know, if you think of Ohm's law, VIR, this is just UO, UO, IF, C min, and all sorts. Where are you? Oh my god. There we go. Okay. There, right. So into chapter 41, we've got the disconnection timetable, and then we have TN systems, and here's the formula there. Okay, so the ZS times the IA must be less than or equal to UO times C min. Okay, let's just get back up. So UO times C min is the 230 volt voltage multiplied by the factor of 0.95, which I think brings it down to 218 point something. Yeah, the low voltage variation. 8.5, right? 8.5. That's all that is. It just changes the V to 218.5. So that is 218.5. Now the IA is the current that we had back in Appendix 3. So when I said we had a C32, in that case the IA is 320. So if we did 320 as the current, 218.5 as the voltage, 218.5 over 320 0.68. It's 0.68 ohms. That is what this formula is about. It's transposition. Now if I go into BS7671 and I look at the tables for the ZS's for the C-type, this is the C-type. There's a 32 amp one there, and there it is, 0.68. So that is how that's obtained. You know, that's just simple Ohm's law. Absolutely simple. Okay. If we were going to measure it, it's the same, except we apply a 0.8 factor to it. And you'll see that in Appendix 3. Right at the beginning of Appendix 3. The whole reason for doing that is obviously to accommodate the change in temperature, because when we're doing a initial verification, we're measuring the earth fault loop impedance. The circuit's not under any load. If the circuit's not under any load, then it's not anywhere near 70 degrees, which is what the operating currents of 320 amp, etc., are designed to work against. So we derate it with a number I can't find. There we go. There we go. Yeah. So think about the math. It's just Ohm's law. Yeah. Resistance is equal to voltage over current. VIR. Okay. But what it's saying is the ZS that we measure. Let me just put this somewhere where you can still see it there while I go on this. So the ZS that I am to measure must be less than or equal to 0.8 times the value of UO times C min over IA. And that's what I did here. UO times C min over IA equals that. But if I multiply that by 0.8, I will then 0.68 times 0.8 get 0.54. And it's not in the regulations, but if you're looking at the on-site guide, you'll see 0.54 given as the maximum measured earth fault loop impedance for C32 protective devices. All right. So what have we covered? And have I missed anything? Let's just evaluate this. We've talked about the need to ensure that ZS is equal to ZE plus R1 plus R2. We've talked about the need to remember that volt drop is equal to the millivolt per amp per meter times the design current times the length over 1000. We talked about the need to remember that the ZS that we measure is less than or equal to UO times C min over IA. And we've also made, just got rid of the ZS bit for normal Ohm's law. We've talked about IB being P over V. We've talked about T equals K squared, S squared over I squared. We've talked about the adiabatic. We've talked briefly about the I tabulated value being the rating factors. The only other formula you may be well aware of is the calculated risk level, but I don't think I'm seeing it in much exams at the moment. But let's just look at it, just to finish off. This is the nonsense that's happening within section 444 for protection against overvoltage of atmospheric origin, the calculated risk level. I'll add anything if I can think of anything else, but for the sake of the exam, I think this is it. Let's go over this. Okay, so it takes a lot more effort in explaining it than it does in doing it, but do not forget, if you are confused about the calculated risk level, there is examples of it in Annex A443. Okay, and that is on page 105. But let's get to here. There we go. Alright, this bit. So, the calculated risk level is environmental factor divided by the LPAL and the, is it the NG? Yeah, the LP and the NG. It's just those things. The environmental factor is easy. It's given to you here. All you need to know is the difference between urban and suburban. The NG is here. You need to know where you are geographically. Again, how would the city and guild put a question in for this? Unless they were to say somewhere that's completely one thing, such as the Highlands, or I don't know. Everywhere's got two types really, so it's hard for the guilds to pick a place. I don't think I've not seen it, and I don't think they would. In regards to this, we're all being motivated to just say one for now, and they just wouldn't approach it. They may, but it's fairly simple with the multiplier. I don't want to add this video to another 15 minutes to explain this, when really you should just spend more of that time just looking at getting rid of that, this stuff. Okay, this isn't in the regs. Okay, let me just, this one, it's not in the regs book. This one, it's not in the regs book. Okay, this is 434. This is Appendix 3. This is Chapter 54. This is Appendix 4. This is part of Appendix 4, but isn't really written down in any useful way. Alright, guys. Yeah. From my experience, I would say the most common formula right now I'm seeing in the exams is this one. I would say. And this one. Alright, and then there may be one calculation or two calculations where you have to do one of these, but I'd say it's a 1 in 5 chance. Alright, but you're more likely to get those other two. Okay, I hope this video's been useful. If you want me to go into more detail on any specific formula or any specific area, just send me a message and I'll have a go at it. Good luck.